Is everyone back? Yes. Okay. So the next thing that we want to show is the Actuatorline app. So this is an example of running actuator lines in VirtualFluids.
Can I ask one question before you?
Yes.
It's just something I forgot to ask about in the last lecture. The force, if I wanted to get the drag or something on the cylinder, is that also like an output you can get, or is it something you have to integrate afterwards? Or?
So yeah, you can calculate something like drag and lift on your surface. You mean something like that?
But now we saw before you could just make you could define the probe points and you get the velocity. Is it possible to define integral forces or?
Not with the probe.
No, you cannot do a sphere probe or something like that, right?
No, not on the geometry.
No.
What about the correct CP, CT stuff?
Yeah, CP and the drag lift thing. So we have special functionality in deep in the code where you can calculate the drag and lift forces on the surface of the geometry.
Okay.
Maybe we have to look directly into it.
Can you still activate it from here?
Yeah, as you can. Yeah, Kite is something else. No, this is
this one. Is that kite drag lift?
yeah, no, kite drag lift.
So you would activate it like this.
Yeah. So if you have the sphere in it, which I can then you can say kite drag lift, and then he will do it for you.
Okay.
And we can also calculate this CP values we have used for a car. So we have a line on top and on the bottom where you get the pressure values for several points.
Yeah.
It's also possible.
Okay, sorry for the interruption.
No, it's a good question.
It's, yes. Okay. So the Actuatorline app. I think I'm going to talk about like why actuator and line and so on and so forth on Friday. So I will not talk about that now, and I just kind of assume that everyone is more or less familiar with what an actuator line is. But I mean, the basic idea is we take a velocity, we have predefined airfoil data, and then we have a lookup table. In our case, we have a lookup table where based on the velocity at the turbine blade point, we compute the lift and drag forces, and then we impose these forces on the domain via body forces. It's a very, very easy way to simulate a wind turbine when the turbine is smaller than the grid, or you don't want to refine the geometry of the turbine because it's too small. So yes, we also have a bunch of includes here. And the important includes that most of them are exactly the same files and classes and so on as the Sphere app. But we have two ones that are a bit specific to our case, and the first one is this actuator line. So there's a class of objects that are called the pre-collision interactor classes, and they are objects that affect the flow. Kind of is the idea. The only thing that is a pre-collision interactor at the moment is the actuator line. And then we have two versions. We have the actuator farm. That is a more general case that is also used for coupling into other codes. And then we have the actuator farm standalone, which can run a turbine consisting of 3 elliptic wings by itself. So it's a very, very simple one. But we decided that everything that's like specific to wind turbines should be as much separated from VirtualFluids as possible. So that we can use different models that just plug in, and we're going to talk very, very briefly about this on Friday. Furthermore, it's called an actuator farm because it's not a single actuator line, but it's always it's all turbines that you will want to include in your simulation on this one specific GPU. You define it in one farm object, and then it does all of these things directly together. Okay, so the structure is more or less the same, except slight differences. So we also have a default configuration file. That's the actuatorline.cfg, and that is in the same app. And then we will go through the parameters as they are called. But if I go down to the main function, so here we have the main function. We initialize the logger, and then we load a config file. But you can also define, when you're calling the app, you can also define another configuration file on the command line. So if I go, no, I can't do that. This is weird. This is the no. Why can't I open it? So I'm here in my build directory again. So if I want to run, I did not. So the problem is that the Actuatorline app is not one of the standard apps that are built, but there's an option for CMake that you build all apps, and that includes the Actuatorline. And then you turn that on by saying VF enable app, all apps, and then you turn it on. VF enable GPU, and then we have to. All right. So if I now run the Actuatorline, if I run it without any command line arguments, it's not going to run because it doesn't find directly the file because it's in another directory. But I can just say I want to run the file apps GPU actuatorline.config, and now it finds it and it runs. So it's a bit, has some flexibility. So we load the configuration file, and as I said, like we have a default configuration file that's written at the top, but you can also choose any other one, and then we run the simulation based on this configuration file. So then we jump to run. So we begin by reading the configuration file and setting all the values that we want to set. So we set the viscosity for air, we set a Mach number, we can read a rotor diameter. In VirtualFluids, all turbines have the same rotor diameter, or like in our current implementation of the actuator farm, all rotors have the same diameter. We set the number of nodes per diameter. Now these are the nodes, the LBM nodes. This is not the actuator line. We call these points to kind of keep it separate. So LBM is nodes, the actuator line has points. We can set an inflow velocity, the same time step start for the output, the time out, and the time where it ends. And also here, these are used for the probes later on. We set a size of the diameter, we set a size of the box. And then here we set turbine positions. So if I go to the configuration file, we set the rotor diameter to 126 meters. This might sound familiar to some of you. If you have worked with an annual 5 megawatt turbine before. We set the resolution to 32 nodes per diameter. And the box is 24 by 8 by 8 diameters. And then here we have the turbine positions. And then we can actually also set multiple turbines directly from here. So we don't even have to change anything in the app to add multiple turbines. And so if you wanted to have 2 turbines in a row, we do it like this, right? And they just have different X positions. This is, of course, the center of the hub. And so here we read this vector. I know these are the pro positions, I'm sorry. Here are the turbine positions, and then there are also positions for point probes. Then we compute the parameters in lattice units, so we divide everything by the respective by delta t and delta x. We compute the delta t based on the Mach number and a velocity that we set. Then we go on to build a grid. So these are, those are kind of the same things that you always have to do no matter what you do in your app. We build it so that it starts at x equals 0, and then y and z are centered around the turbine. We don't have any periodicity, and then we build the grids. Maybe also, I think this was kind of swallowed last time, there's a certain order that you have to call these in. So you have to add the coarse grid, then you have to set the periodic boundaries, and then you have to build the grids, and then you set the other boundary conditions.
You need the information of the periodic boundary condition to define the neighbors in the correct way.
Yeah. Now I jumped. Okay, here build grids. Okay, and then we set the parameters of the simulation. So now we have the domain. Now we set the parameters. So our reference length kind of is the rotor diameter. So this is when we compute the Reynolds number later on. We want to have files. These are the same. We initialize the whole domain to a constant velocity of velocity LB. This one is important when you're using Actuatorline. So normally VirtualFluids does not allocate a field of forces in the entire domain because not necessary. But if we use for the Actuatorline, of course, it is forces, so we have to allocate the force field explicitly. Well, not entirely explicitly, but we have to tell it that we're going to use it, and that we do by set is body force. So now we have a force field that we can write stuff into, for example, an Actuatorline, or if you have other things. We define all boundaries except the outflow boundary to be velocity boundaries. And we use this velocity with pressure interpolated compressible and the non-reflective outflow boundary condition. A thing that I'm also going to go more into detail on Friday is the turbulence model. So we have a turbulence model factory, which is kind of like the boundary condition factory. You first decide what kind of turbulence model you want, and this is kind of the outside perspective. This is the user world. So we have the factory, and then we can actually define this in the configuration file. And you will find that here in the configuration file you have this entry turbulence model, and this is always the same. So this is actually one of the few things that I read directly from the configuration file. If you don't have to write it explicitly in your app, you just pass it to the turbulence model factory, and then it will read this turbulence model key, and then you choose one of the 3 available ones, and then you also set one of the so far all the turbulence models that we used only have one constant, so we just call it the subgrid scale constant. and then there you go. And also is something that we use, since we use an explicit subgrid scale model, we don't need an explicit stabilizer from the cumulant. So we turn off the limiter that we talked about. So we don't have the stabilizing mechanism from the cumulant, and that you do by setting the limiter very, very high. So we usually do this unless you use refinement. If you use refinement, you need the limiter. Don't know why.
What happens if you don't do this with high values? Is it getting too viscous, or what is happening if you don't turn it off?
Yeah, I mean, you add hyperviscosities, right? Oh, it changes. It looks different, but not very different. But we think in our experience, at least for atmospheric boundary layers, this is the most accurate way.
So actually,
implicit with explicit.
It turns off the super convergence. I mean, if actually the limiter, if the reduction of these relaxation rates actually takes place, then the super convergence is turned off, and then yes, this is like you're having some hyperviscosity, so you have more dissipation.
So it's a little bit like, I think in ellipsis you have this value where how you can choose between first or second and third order advection schemes, right? And the limiter is roughly a similar thing that you can make it more dissipative or less dissipative but more accurate. And if the higher you set the limiter, the less dissipative it is. And since we have an explicit subgrid scale model, we don't want any additional dissipation from the numerical scheme itself. We just want to use QR's viscosity. So that is our argument, like our thinking behind this, and we see that this has been pretty accurate. But this has also not been investigated in a very parameterized way or anything like that. This is just from like our own experience playing around with it a bit. Okay, so then we have a turbulence model. So it's time to add a turbine, or however many turbines you want to have. We define a smearing width for the actuator line. We use the recommended value, well, as some recommended. Then we said we need to now set a density. We set it here explicitly and not use the one that is used that you can define as from the parameter. And there was a reason for that I cannot remember right now. Then here we say this is how many points we have in the actuator line. Now we actually did call it nodes, I see, but that should be changed. So this defines the discretization of the plate. And then in the standalone actuator line, you can only set a constant TUBS ratio, as it is right now. And then actually you have to define a number of rotor speeds, and I believe this number has to be the same as the number of turbines that you have. And then you create a
Sorry to interrupt, but can we easily add this to the config file, the TUBS speed ratio?
Yeah.
Okay, so it wouldn't like crash if we choose a different number than 7.5.
No, but I mean, of course, now at the moment you would have to write the config.
Exactly.
You have to read the config file and so on. But I guess within reasonable limits, it's not gonna be a problem. I think I computed as long as the TUBS-speed ratio is under 15, and the actuator line doesn't skip a cell in one time step. So the maximum you can set is 15, basically, without any problems. Because at that point, the time step requirement for the actuator line, that the outermost furthest point doesn't skip a cell in one time step, then this becomes more restrictive. But until then, LBM is the more restrictive time step. Okay, so we build an actuator farm object. We make a shared pointer again, and we pass in all these values. Importantly, there's so the actuator line must, because we're lazy, the actuator line must exist on one level. So it must not skip levels. Or like switch between levels. So there must be a constant refinement in the entire area of the actuator line, and we have to set this one explicitly. Actually, if you mess up, it will tell you that it's going to complain that it didn't find any points. And so then we have our actuator farm, and now we can add it to the simulation by adding one interactor to the actuator farm. As I said, the interactors are everything that affects the simulation itself. And then we also have this very neat feature, I think, that Anna thankfully implemented, is that we can have some paraview output directly from the actuator line. So we directly get the location of the points and I think the velocities and forces. Well, there's no more to an actuator line, I guess, than velocities and forces. So we get a paraview file later on that tells us exactly that. Then we can visualize our turbine directly. And then here we also add some more probes. So I add a probe plane. I think those are at like various distances downstream of the turbine. One before the turbine, one after the turbine, and one then 3 diameters down from the turbine. And also one vertical and horizontal, like cut through the entire domain. And then also here we use the time series feature. So I had these probe positions in the beginning that I defined. So these are point probes I place in the domain, and they will write like a time series output. So for example, if you wanted to compute, the idea was that if you wanted to compute spectra in the flow, you need a time series. We can't do this online, so that's what that is. That's why we implemented it in the first place. And then we print some output and we run, and hopefully it works. So I can run this now. And so yeah, here I think we didn't go through the output before, but VirtualFluids of course also talks to you, and which one are we here? So it tells you which config file it used, tells you how big the grid is. So this is this grid has 50 million nodes. Tells me how large the velocity, the boundary conditions are. It tells me which subgrid scale constant I used, which turbulence model I used. So what happens often is that you run a simulation and the result is not what you expected. I don't know if you had this. But so each one of these comes from a lot of sweat and tears when we try to run something and change something and didn't affect anything. So at some point we decide, oh, let's output what we actually used in the simulation, and you see, well, your subgrid scale constants was 0 the entire time, and that's why we print it now. So here it also tells you which kernel you use. And here this is the memory on the GPU that you're using. So this case uses 10 gigabytes, 50 million nodes, roughly 10 gigabytes of memory. And this is pretty linear in my experience. So we run, here we actually have the word length. So So,
Question.
yes,
The Reynolds number that is here displayed in the output,
yes.
like, it's possible that it's not always the same one. Like this is the actual case Reynolds number, right? Because sometimes it seems it's also the grid Reynolds number that is displayed.
I actually don't know what it is.
Okay.
This Reynolds number here. This is the grid Reynolds number.
I mean, this is how you define it.
Is this based on these ones?
This is how you define it in the code.
On this one?
Where does this 126 comes from?
I put that in. It's the roller diameter.
I thought it's the Reynolds number for the rotor diameter.
Yeah. It looks for me like.
Somewhere in the code you have to calculate the Reynolds number.
Yeah, but no, but this happens now automatically in this.
Okay.
What's it called? In that outputs. These I didn't put this out.
Okay.
And this is done automatically nowadays.
So it is somehow in the locker.
Yeah. Okay, so now it ran. You don't know this, but if I don't use an actuator line, I get around 3,000 mNOPs. With the actuator line, I get like 2.7 or 2,700. So there's, in this specific case, we roughly lose like 10% of performance for using the actuator line. But yes, that's the price we have to pay. If I now go to build output, here is my output for this simulation. So those are the results, and here these are the results from the actuator line itself. So this will include the points and velocities and forces and so on. Now, let's see if I do this. If I can.
Just a question with the compilation. So you said it's DO. So I'm running the CMake preset make GPU Q and then or GPU and then what do I need to do after that?
Which command did you use?
Give me a second. Does this work? That's our computer. No, wait, I'm on the other computer. Wrong. So the command for running the CMake. I can show you in a second.
Yes.
It's 1.56.
So, okay, maybe this is enough. Okay, I should do this. And then I don't know. This one. And then this one. Changing the starting position. And now I'm crashing my entire computer.
Because they just no, this will explain why fun you can make fun. But here in this example, this is also good with fun. But in the example that he shows in the line, you just have like one type of thing.
Which is supposed to be this one.
He use a lookup table, but he's just like using a standard form and table. For the actuator line we're talking. That's what he's doing. It works. We got the
and then so I now opened the actuator line. This is now the output from the actuator line, and you can see here I can choose the forces or the velocities, and then here I have the probe. Unfortunately, the probes are only points; they're not surfaces, which is not super pretty, I think, but easier. So
So the probes in the Actuatorline, they actually are using some interpolation inside the lattice-Boltzmann grid, or?
the probes not, but the points of the actuatorline, yes.
Yeah,
They use a trilinear interpolation.
Okay, so try.
Yeah. So yeah, here we see our. Now I don't have multiple time steps, unfortunately, so I can't show you the turbine turning. But well, okay, I can download some. I only have 4 time steps, anyways. Yeah. Okay, now you can see the turbines go. Wonderful. Turbines turning.
Nice.
I mean, that's what we're here for, right?
Yeah.
And yes, just give me a second. And plane probe horizontal. Download the wrong file.
Is there also like a PVD file that manages all time steps?
No, not for the probes. I think for the output, not either. Right? For the whole domain output, there's not a PVD file in the GPU version.
Oh, I guess there is.
There is?
I'm not sure. There's not a PVD file, wait.
Bit unclear.
Output.
Plane probe horizontal. Where's my plane probe?
There should be a
So you
PVD
just,
file.
this was 50 million cells, and you just ran this now.
Yes, right? Yes. Wait. This is not. Lass uns das runterladen.
We're missing a PVD file.
Ja, das ist eine Zeitserie, so Paraview.
Ah, no PVD file, no.
Now, here we go. So, and you can also see now we have the average velocity. This has not converged yet, as you will be able to tell. No, shift is no. I'm really not the expert in Paraview.
So you can pick one of the presets here on the coordinate presets.
Yes, these ones. Yes, exactly not these ones.
Yes.
But this one. Well, yeah, exactly. So here's our the wake. Break up the wake. You see how yeah. You know what this looks like. Many of you know what this looks like. Of course, as I said, it's not yet converged. The averages, but you can, yes, as I said, you can have the means, and you can also have the variances. The variances, great. I think they're not initialized yet because it's only the first average, but you get it. So yeah, this is a Actuatorline. And it.
Just
Yes, I hear
It's
you.
like the same blade, right? Always in here.
Sorry?
It's like the same blade that we have.
Yeah, it's just an elliptic wing because then you don't. That is, you can compute the lift and drag
Yeah, without
without any. Yeah.
Because I was looking for the look at table.
No. There's no. The standalone is really the dumbest way you can do it. But it's. Yeah. I don't know. Yes.
If you put the second turbine now, into the concept file, it should pop up in this field too, right?
Yeah.
Okay.
So I didn't test this at home. So yeah, exactly. I'm a bit skeptical of venturing into uncharted territory. But let's see. 7, 6, 8. Do I need a comma there or not? Or does it? I think I don't, right?
If it's a vector and this is a configuration file, then you don't.
Yeah.
No comma.
No
You
comma.
only
No comma.
get values.
No comma, and I will have to set a second rotor speed.
But well, the vectors are composed of 3 tuples. I don't know if you have another
No, this is like a.
It's completely.
tuple 3
What
element.
is it called?
No, I guess he's just adding
Yeah, with this
a
one, the
new
get vector,
ring.
Get vector then.
and then turbine positions X. Like this also, like this is a list. It just
But
can be.
when it's real, then I don't know if it's going to.
No, I just believe you can
Because real
cast
is
it to real.
Yeah, it's not a
You
vector.
just add a 0.
Could be. I want to say that real maybe is a scalar value,
Yeah.
so it accepts only one.
Yeah, it's one per. Yeah, but it's it can be a list of one values.
Okay.
Yes, I think.
I use vector.
I have to do this a little bit differently. You do this, and then like this, right? Just gonna work.
So this copies the rotor speed.
Yeah, this is not going to be a vector of the same length as the turbine positions.
And if you don't do it, then it's considered that the second actuator line is not rotating.
I honestly don't. I thought it would throw an error, but it didn't. So
It didn't.
yes, I know. That's why I'm a bit confused. So doesn't say anything about the number of turbines. That's an output we should probably add in the actuator farm. Yeah, and yeah, I think many of us have also the goal to make VirtualFluids a bit more expressive in a way, that it tells you more
Yeah.
what it does. But you know, it's a very nice project for someone starting up to work on VirtualFluids.
Do you hear this guy?
It's a very, like, you know, I can show you exactly where you have to put the line. You just have to put yourself.
Just meaning it's 2x.
So yeah. Also for, you know, if you're running VirtualFluids, this is the last line, and then it starts running. So if you don't see any output after, if you don't see this line, well, of course, maybe it says a different GPU. But if this line does not, like, if nothing comes after this line for a while, no worries.
Yeah.
If it doesn't reach this line and nothing comes, worries.
What did you do there? You wanted to add another turbine and you had to change the code?
Yeah, now I wanted to, yes. Yes.
So the code is only made for one turbine.
This app, yes.
This
It's app,
specific
yeah.
app, yeah.
Yeah.
Okay, so yeah, it's called an actuator farm because it's a farm, it's a wind farm. The wind farm may consist of only one turbine.
Okay.
But yeah, I mean I can open it. Oh God. Many issues. So now you see that I added a second turbine and the performance took a tiny hit, but it's basically the same as it was before. What did I want to show here? I don't know.
Can you show again the time steps you specified in your config file?
Here? Yeah, it's every 100 seconds.
So it
It's
should
2 steps.
time steps.
Yes.
Like,
It's not seconds, is it? Or is this seconds?
This is seconds.
Is this 1 time step per second also?
No. This is, we specified this config file is entirely in SI units.
Okay.
And then it's converted here. Here. So that's why we call this timeout and this is time step out.
Okay.
So if I go into builds and then 3958, right? So let's hope that yes. There is the second turbine.
But you also have to show the flow field.
You're the chosen one.
Actuatorline. We don't have this flow field, but we have the whole domain. But this is going to take a while. I think this is still yes. So there was a second turbine here, and that's why. So this is the wake of the first turbine, and here's the wake of the second turbine, and we see that the wake deficit has increased. So the physics, it's the same physics as we expect. Okay, I think.
Can you show the compile flags?
Yes, sorry, yes, exactly, the compile flags. So it's the VF enable all apps. All the compile flags in VirtualFluids now start with VF, and then they usually VF enable something. So VF enable GPU, VF enable double precision.
Question, what's the difference if we choose the preset option, where we say make GPU? Is this like a predefined set of compiling flags?
Yeah, exactly.
Okay.
And I think it's basically this one. And then you can actually look, you find these in the CMake presets.json.
Yes, but this one isn't included, I guess, because it's manually.
No, it's down here. Make GPU. And so it builds the GPU version, and then it also makes the unit tests, and it uses it creates a make file so that you can run make afterwards. But if you were running it on Microsoft on a Windows computer, you have to use the MSVC, and then you have to configure it slightly differently. So if you go here, inherits from GPU. Yeah. For example here, the unit tests means that the VF enable unit test will be set to on. And the GPU one means that VF enable GPU will be on and VF enable double accuracy will be off.
So then actually we could extend this and add the command set for the actuator line.
Yeah, exactly. So I have I have this like a little way more options, and then you can set it even more precisely.
Okay.
Yeah. So yes. So I think that then it's back to you, Martin.
Okay,
Yeah?
small break and